The liquors that dyers employ to tinge are qualified to do so by multitudes of little corpuscles of colour, insinuating themselves into and filling all the pores of the body to be dyed.
Those words come from a book published by the English physicist Robert Boyle. It was written in 1664 and was the first book to discuss the science of coloration. But even today, the words remain a good description of the chemistry of dyeing. We've come to ICI Blakely near Manchester, where dyes are made and tested before being marketed throughout the world. Each industry requires different properties in the dyes that they use, and so the large dye-making concerns like ICI provide technical service and advice to their customers on the selection and use of their products. And here are the products. A large range of fabrics colored with many different dyes. The range of colors we have is demanded to us by fashion because we want clothing that's more interesting and varied than we've ever had before. A lot of the colors are azo dyes. And over here, the machine is a roller printing machine, and it's printing red and orange azo dye onto cotton fabric. The subject of this program, then, is the chemistry of azo dyes. So if we're interested in azo dyes, we're going to have to be interested in finding out how those dyes are incorporated into the fabric. After all, there's a lot of different fabrics here. Cotton, polyester, rayon, silk, all these need to have dyes incorporated into them. Well, the roller printing machine incorporates dye on a large scale. But sometimes dyes need to be incorporated on a fairly small scale. This fabric here, which has a red, a yellow, and an orange azo dye incorporated into it, this fabric was printed by a silkscreen technique.
Essentially, we're looking at a long table, which is covered with a special adhesive so that the fabric can be ironed on and kept in place during printing. The so-called silkscreen is nowadays a fine nylon mesh onto which a pattern has been applied by a photographic process. Most of the screen is impervious, and when the dye is applied in the form of a fairly thick paste, the screen functions as a stencil. Only the pattern is printed onto the fabric, and in this case, an azo dye is being used. Many azo dyes have been formulated here at ICI Blakely. After synthesis, of course, their suitability for dyeing a range of textiles is tested in small vats like this. Here's a new red azo dye. But there's a vast range of azo dyes, both new and old.
The red dye in this bottle is over 100 years old. It was made by a man called Peter Grease, the discoverer of diazo compounds and azo dyes. Although he was born and studied in Germany, he spent most of his working life in England, first doing research at the Royal College of Chemistry in London, and then for 25 years as a brewer's chemist to the firm of Samuel Allsop and Sons in Burton-on-Trent. How much time he spent working for the firm is debatable. He published about 140 papers, only one of which was concerned with brewery chemistry. The rest were all about diazo compounds and azo dyes. He was acknowledged by his fellow scientists and made a Fellow of the Royal Society. But he never really reaped the financial rewards that could have come from the synthesis of azo dyes that had useful application. His interest in pure research seemed to prevent him from making the transition from dyes that were nice colors to dyes that could be used to dye fabrics. It could be said then that this provides an example of Peter Grease's lack of technical perception. But Grease, after all, was a brewer's chemist and not part of the dye-making industry. Well, he might have been surprised to have discovered the application that his research has now found. There are over 2,000 azo dyes in commercial use, and this represents about 60% of all the dyes that are made. They're used not just for dyeing fabrics, but for colouring things such as paper, soap, cosmetics, and even food. So let's take a look at a reaction that Peter Gries might have been doing over 100 years ago. The reaction's called a coupling reaction. So you won't be surprised to see two solutions here. The one, a primary aromatic amine, and the other, called a coupling component. In this case, it's a phenol. Now, the interesting thing that Peter Gries discovered was that you could take a primary aromatic amine and convert it into a stable diazonium salt. But to do that, the temperature has to be low. So I'm going to add some ice to the primary aromatic amine. Let's get that out of the way. And give it a bit of a stir. And then react the amine with nitrous acid to form a diazonium salt. Stir it up again. And now let's do the reaction. Here's the diazonium salt, and over here, stirring, is the phenol. Let's add the one to the other. Well, there's an instant color change. I'll just add the rest of the diazonium salt, and you can see the full effect. Well, that's quite a change. And when chemists observe that sort of thing, they ask themselves several questions. Given that they know the structure of the reagents, they want to know what the structure of the product is. And when they know what the structure of the product is, they're interested to find out what the mechanism of the reaction is that they've just done. So let's take a look at the mechanism.
Our starting point is the amine aniline and the chemistry of its conversion to a diazonium cation. The reagents we use for this conversion are hydrochloric acid and sodium nitrite. These reagents provide a source of nitrous acid, and it's this acid which is involved in transforming the NH2 functional group in the aniline molecule to an N2 plus group in the diazonium cation. In terms of the mechanism of this reaction, we need to take a closer look at the nitrous acid molecule. The nitrous acid can be protonated, and the resulting intermediate then loses a molecule of water to form a nitrosonium cation. Although not firmly established, it's thought that in highly acidic solutions, the first step of diazotization involves interaction between the amine and this nitrosonium cation, which acts as an electrophile. Given this, the sequence of steps that follows involves first loss of a proton, then rearrangement of the molecule to form an intermediate species that after protonation can eliminate a molecule of water and form the diazonium cation. Let's look at the diazotization again. Attack of the electrophile, loss of a proton, rearrangement of the intermediate, protonation of the OH group, and elimination of a molecule of water. Well, that's how a diazonium cation could be formed. What about the mechanism of the coupling reaction between this cation and phenol to form an azo dye? The reaction is carried out under mildly basic conditions, so the acidic phenol is ionized and exists in equilibrium with phenoxide ion. This time, reaction doesn't occur at the functional group on the benzene ring, but on the benzene ring itself. Attack of the diazonium electrophile forms an intermediate, which can then lose a proton to form a substitution product. A dye which is characterized by the presence of an azo group and which is formed by an electrophilic aromatic substitution mechanism.
So there's a simple reaction that illustrates what we're trying to teach. What I want to do now is to show you the reaction of a single diazonium salt with 3 different coupling components. So I'm going to have to make my diazonium salt again. Here's the amine sitting with some ice to keep it nice and cool, and I'll diazotize it. Stir it up. Add the sodium nitrite, and there, hopefully, is our diazonium salt. Let's add it to the 3 coupling components. Here's the first. The second. And I think you can see there a color change occurring almost immediately. And here's the third. Well, the coupling components, as you saw, were themselves already slightly colored. And so to convince you that the reaction's taken place, let me do the reaction again, but this time in a slightly different way. What I've got here is a filter paper on which I've smeared the 3 different coupling components. And what I'm going to do is to simply run the diazonium salt down the filter paper. Let's do that again. And I think you can see there we've got 3 definite, different colors. Let's look at the middle reaction. Here it is. And you can see now we've got an orange azo dye. Let me stir this up a bit more. It's really precipitated out. And there's the orange dye. Well, this coupling component was beta-naphthol. And what I want to do now is to work you through the mechanism of that coupling reaction.
Don't be confused by the prefix beta in beta-naphthol. It just refers to the position of the OH group in the naphthalene ring system. Notice too that the diazonium cation contains a sulfonic acid group. Given that we know the mechanism of the coupling reaction, we can anticipate coupling to occur at either of the 2 positions ortho to the OH group, or alternatively in the para position. In fact, only one of the possible products is formed. Attack of the electrophile occurs at only one of the ortho positions in the naphthalene ring, giving an intermediate which loses a proton to give the orange dye called orange 2. We have more to say about the specificity of this coupling reaction in the broadcast notes. This dramatic appearance of colour is again brought about by azo dyes. In this case, though, the coupling component has been impregnated into the cloth and the diazonium salts in the solution. When the coupling reaction takes place, an insoluble azo dye forms inside the pores of the fabric. But in order to transform coloured organic molecules into useful commercial dyestuffs, we need to devise methods of application and techniques for incorporating the dyes into the fabrics. Vivian Stead.
And when the coupling component meets the diazo component, an insoluble dye forms instantaneously. And it's trapped inside the pores of the fibre. Here, we're making a dye stuff, we're making it insoluble, and we're going to rely upon mechanical trapping in the fibre to give us resistance to washing. This was the basis of the azoic method of dyeing cotton, in which the mechanism was just to retain the dye by physical trapping in the fibre.
But both samples are cotton. What of dyeing other fabrics? What other mechanisms are available? In the bath are 3 dyes, and the flag is made of 3 different fabrics.
Each fabric has different physical and chemical properties. Each will want a different type of dye stuff. For instance, at the bottom here, we've got silk. Silk, a long molecule with pendant amino groups. Those amino groups can form a salt, the dye stuff which contains a sulfonic acid group. So you can retain a sulfonated dye on the fibre by means of a salt linkage. The second fabric here is cotton. Now, cotton has no pendant amino groups. The only chemical groups which stick out are hydroxyl groups. But of course, hydroxyl groups are capable of forming hydrogen bonds with atoms such as nitrogen, which will donate electrons. So if we build ourselves a nice long molecule, studded here and there with nitrogen atoms, we'll be able to hang on to the cotton by hydrogen bonding to it. Those are 2 chemical properties utilized. In the middle, cellulose acetate. Nothing in the way of chemical properties. Its hydroxyl groups have been acetylated, but with an interesting physical property. When heated, it softens slightly. It's capable of literally dissolving a small dye molecule. So if you have a small insoluble molecule dispersed in the dye bath, it will dissolve it and form a solid solution in the cellulose acetate. Let's have a look how our flag is getting along. Take it out, it looks pretty murky at this moment. Just give it a rinse. Out, perhaps. Another little rinse. And that's had about a couple of minutes. Not long in terms of a dyeing process, but that's how it looks. If it had had 10 minutes, it would have looked like this. And there you have 3 different fibres, each selecting from a mixture of dyes in that bath the dye which has been specifically tailored to meet its own physical and chemical requirements.
In virtually every dyeing process, it's necessary to ensure that the dye does more than just colour the surface of the fabric. We've got to ensure that it penetrates into the fibre. And then the problem is to ensure that it stays there. That's particularly important with washing and cleaning. Washing and cleaning a fabric can wash out dirt, but it can also wash out our dye. So when you've got a situation where you're using a water-soluble dye and a fabric like cotton, there's the danger that the dye will wash out. The fabric will fade. That's a situation you may want on some occasions, but not all the time. Vivian Stead's shown us 3 different fabrics: silk, cotton, and cellulose acetate, each of which selecting out a specific dye from a dye bath. And that tells us something very interesting about the way dyes interact with fabrics. If we can get some information about the structural features of the fabric we want to dye, then we can design and synthesize a dye that will be suitable for dyeing the fabric. In the first example he showed us, he used silk. There, the molecule of silk contains large numbers of positively charged ammonium groups, NH3+ groups. And so, if we introduce into the dye an SO3 minus group, a sulfonate group, then that negative group, negatively charged group, can interact with the positively charged ammonium group. The positive and negative charges ensure that the dye stays bound to the fabric. In a man-made polymer like polyacrylonitrile, the acrylics that are used for knitwear and furnishing fabrics, the situation's slightly different, but not very, because there, the charge group within the fabric is a negatively charged group. And you won't be surprised then that the group we introduce into the dye is a positively charged ammonium ion. And given that, we've got our ionic interaction between the dye and the fabric again. In the second example, we looked at cotton. And here the surface of the fabric contains hydroxyl functional groups, OH groups. And the interaction we take advantage of is to introduce an amino group into the dye. Then the nitrogen on the amino group interacts with the hydrogen of the hydroxyl via hydrogen bonding to ensure again that the dye stays on the cotton. And in the final example, imagine this to be a model of cellulose acetate. It could be polyester as well, but these kind of man-made fabrics don't have any chemical groups which we can interact with. But they do have a particularly interesting physical property, and that is that when they're heated, they melt. And when melted, it will dissolve up a small azo dye molecule. So our azo dye molecule, if it's water insoluble, will dissolve into the man-made fiber. This program has been concerned with the chemistry of just one group of synthetic dyes that add color to our world. I'm in black and white now, but don't adjust your sets, because if we gradually introduce some color, though we may not agree on which colors we prefer, I think we would agree that having color there in the first place makes life somewhat more enjoyable.